Hey, what is up guys? Welcome to another video on data structures. In this video we are going to discuss about in-order traversal of a binary tree. Now from the video from the previous video we have discussed that in-order traversal, the order in which we traverse a binary tree is we have left, then we go to root, and then we go to right. So if this is a binary tree that we have, and this is the root starting position, then we will explore its left first, then we will explore the root, and then we will explore the right. And since trees are recursive in nature, so for example, if we have something like this and this is the root, so going towards the left of it, we can see that this part in itself is a tree in itself, right? This part is tree in itself. So basically trees are recursive in nature, and hence writing the recursive code for trees is comparatively easier than the iterative part. And in this video we are going to discuss about the both. We will first see the recursive code, then we will see the iterative code, because recursive code will simply tell us the instruction, but iterative code will force us to think about how this recursion is actually working. All right, so let's discuss, let's start with the recursive one first. Now now for recursive code we have a basic structure for every recursive code. First we have the base case, right, base condition, which will tell us when the recursion should stop, and then we have computations या फिर further calls. This is the basic structure of every recursive function that we have. Okay, so writing the recursive code for this in order traversal, we will discuss about this base case in a while. Let's first discuss the computation. The computation is very simple. We will just follow this particular thing. Let's name the function as void in order, and as an argument we will have the root, right? Okay, so base case we will see in a while. First let's discuss about the computation. So the first thing is we are exploring the left, right? So if this is the node, then we are going towards the left first. So what we will do, we will explore the left first. We will make the recursive call for the left child. Then we will process our current root, and then we will make the recursive call for the right child, right? So this is the order, and this is nothing but what I have written here. This is the exact translation of this. Talking about the base case, now let's see this particular example that we have, right? Now according to this particular code, we will start from here, then we will go to its left, then we'll go to its left, and then we will go to its left. But the thing is, there is no left, it's null, right? So this is the point where we should stop. We should not go further left of this when we have null. So this will be the base case only. So we will write if root is null, then just simply return. And this is simple in order traversal code for recursion. This is as simple as that, and it is even simple to memorize. If you don't even understand the logic, you can very simply memorize this, but it is not recommended for at all. Let's talk about the time complexity and space complexity that is required in the recursive approach. For time complexity, we are exploring every node once, right? So it will be number of nodes, theta of number of nodes as time. Talking about the space, since here you can see that there is no space that we are taking as such, but the thing is, whenever the recursion is involved, we are taking some space from the function call stack. So whenever we are having a program, we have a function called stacks which remember the function calls, which remember the parent call. So basically, if we are at this part and at this particular line we have called this particular node, then we need a stack to remember that once the process of this call is over, we have to resume from this particular node only, this particular function only. So for that we need a function called stack. Also, we also need to remember from which particular line we need to start the execution once the return is control is returned back. So this is that is an external overhead that we require whenever we are dealing with recursion. So if you're talking about the space complexity, maximum space that can be taken from for a particular at any time of the span of this code will be the height of this binary tree. Height of this binary tree. This will be the maximum space. So big O of space is this, right? Now this was the recursive code, but the thing is, whenever we are having a iterative code which takes exact amount of time and space, is still considered better than the recursive code, because in the recursion we have the extra overhead to remember from which part should we start, should we resume the previous function, right, as we have discussed just now. So iterative codes are always preferred over the recursive codes. So now here we will see the iterative code for the Inorder Traversal. And this iterative code will also force us to think little bit outside of the box, which recursive code was not forcing us, because trees are recursive in nature. So for iterative code, we have to remember that we have to go to the left deep node, then we will have to explore the root, and then we will have to go to the right deep node, right? So this is the tree that we have, suppose, right? Okay, now let's try to build the logic. Okay, now since we have just seen that we have to go to the leftmost deepest part, this child from this node, so what we will do, we can have a while loop, right? We can have while root is not equal to null, we keep on going towards the root is equals to roots left, right? We can have this part, right? Basically we are going towards the left. So if you try to dry run this particular piece of code, we are at this part. Now root is not null, so we'll go to this, then we'll go to this, then we'll go to this, and its left will be null, so it will stop here. But the thing is, we also need to remember which is the node that should be processed after this is encountered as null. So for that we will have to have another structure that we will take it as stack. Why we took stack, I'll just explain in a while. See, stacks are first in and last out order, right? LIFO, you can say last in first out, it's all the same. So this is the node that let's name them 1 2 3 4 5 6 7 8 and 9, right? So the one will get into the stack in the beginning, and it will come out at the end, right? So this is the type of structure that we are following. And even in recursion also we are we are using the function called stack. So in any way we are using stacks when we are dealing with this traversal. And now here we will store whichever node that we have explored. So we will stack dot push root, right? So let's try to dry run. Now. This is the stack that we are having st. Okay, so we are at this particular node, right? We are at this particular node, so we will store it and go to the left, right? Then we will store it, go to the left, then we will store it, go to the left, and then we will store it, go to the left. Now we have null, so the condition will be false, the loop condition will be false, and we will come out of the stack. And now our stack is having all the order in which we have to explore. Now the left part is over, right? This left part is over. Now we have to explore the root. Since root currently is null, what we will do, we will take the top element from the stack as the root. So it will be st dot top, and we will pop it out from the stack. So this is taken out of this stack, and it will be processed this is the C++ code, by the way. And then we will go and explore the right. So we will go and we will see root is equals to roots right, if it exists, right? And this is it. This is the code. Now once we are at the right, suppose we are at this particular node, okay, and let's make some left here also. Okay, so we are at this particular code, right? And we just came back from this part. So our root will hold the value of 2. It will be popped out. Now we will go to the right, we will go to the right. Now we are at 5, and then we again need to go its left, right? So we have to start this entire process once again. So for that we will put this entire thing again in a bigger loop. Okay, so now let's write the code using this logic. To start with, we will have the function. So we have void in order node star root, right? We will have this space from the stack, right? Then we will have a bigger loop while stack dot empty is equals to false, or root is not equal to null. So initially stack will be empty, right? So when the stack is empty and we still want to go inside the loop, that is when this particular condition will come in handy in the initial case, right? And now we will go inside this loop. This is the operations that we will follow, and after that we are simply out. That is it, right? So this is the in-order traversal of a binary tree. This is the code for that. In the next video we are going to discuss about post-order and pre-order traversal of the binary tree. Yeah.